Greetings everyone and welcome back to General Chemistry. Our topic for this video is going to be nuclear chemistry, so let's get started. So before we begin, a little relevant story. Well, I think it's relevant. So this right here is a 9-volt battery, and I know what you might be thinking. We already talked about electrochemistry and batteries in the previous video, but I'm not here to talk about the battery specifically. I'm more concerned with what this battery is for, which of course most of you know is a smoke alarm. So smoke alarms, many people don't know this about smoke alarms, but smoke alarms actually use a radioactive element, which is americium. Element number 95, americium, named after America, of course. Americium. And there is a story, you might want to look it up, or maybe if I have the free time I'll post a link to it in my usual pinned comment. But there's the story of the radioactive Boy Scout who died just a few years ago, actually, in prison. You'll understand why he was in prison soon enough. So the story of the radioactive Boy Scout goes something like this. You had someone who, even when he was a very young boy, he was very interested in science, and he would do all these experiments at home, and you know, he was just really into doing all sorts of experiments, and he even hurt himself several times conducting his experiments, but that never deterred him, and he just kept on pressing forward, and eventually he got interested in making a mini nuclear reactor at home. So he needed some radioactive material, and of course you can't just order that from Amazon or anything like that, so he had to get creative, and one of the things he did was he bought a bunch of smoke alarms and extracted americium from them. He still didn't get enough americium to do his experiment, so he had to go to other sources to get more radioactive material. But yeah, if you ever find yourself buying a bunch of smoke alarms, don't be surprised if the FBI comes knocking on your door. With that little story out of the way, let's go ahead and talk about the meat of nuclear chemistry. Let's talk about the nucleus. So, of course, the particles within the nucleus are referred to as nucleons, and there's two types of nucleons. You already know what they are. Neutrons and protons. Neutrons and protons. So if I say I'm looking at a nucleus that has two nucleons, it could be two neutrons, or it could be two protons, or it could be one neutron and one proton. So nucleons, just a general term that refers to the particles within the nucleus, regardless of whether they're neutrons or protons. So we learned about Coulomb's law back in video number 10, I believe, when we were talking about interparticle forces and what was it? Hold on. It's coming back to me. Lattice energy. When we were talking about lattice energy for ionic compounds, we said lattice energy was related to the Coulomb force, and the Coulomb force, also known as the electric force or electrostatic force, was equal to some constant times the first charge times the second charge divided by the distance between them squared. And this allows you to calculate the force between two charged particles. So if I had two protons inside of a nucleus, then of course their charges are equal, so you've got a constant times the same charge times itself, so that charge squared, divided by the distance between them squared. Now this is the more important factor to worry about, because in the nucleus, they're really close to each other. This distance right here is really small, and the smaller the distance is, the more you're dividing by a smaller number, the greater the electrostatic force, the stronger the repulsion between these protons. So how is it that you can have so many protons sitting inside the nucleus really close to each other, and yet they don't just kind of repel each other outward and fly away in every which direction? Why is it that nuclei are relatively stable? What is it that keeps them intact? Two factors. One of them is the neutrons. So what the neutrons do, even though they don't have any charge that can pull the protons and counteract the repulsion between them, what the neutrons can do at the very least, despite not having a charge, is that they can put some distance between the protons. If they just stick in between the protons, they can help keep them further apart. The further apart they are, the weaker the electrostatic force between them. So that's the basic function of neutrons. They're just there to create gaps, to create some distance between the protons and reduce, but not completely eliminate, the electrostatic force between them. The other factor that helps keep the nucleus intact is what's known as the strong nuclear force. So there's a force that helps keep these protons together, known as the strong nuclear force. And the particles responsible for the strong nuclear force, you don't really need to know about this for chemistry, but the particles responsible for the strong nuclear force are called gluons, and those can also be found in the nucleus. Again, you don't really need to know about gluons for your typical chemistry course unless you have one of those instructors, but you know, it's a simple FYI, so there it is. So that's ultimately what keeps a nucleus intact. Of course, even with the presence of the strong nuclear force, if you have too many protons and too few neutrons, if you don't have the right ratio of neutrons to protons, then you'll still end up with a relatively unstable nucleus. And an unstable nucleus doesn't necessarily just split apart and fly apart, though there are some nuclear reactions where that's exactly what happens, where one big atom splits into two or more. Usually what's going to happen, well, I shouldn't say usually, but in many cases you don't need to go as far as splitting the atom if you have an unstable nucleus. Sometimes an unstable nucleus will undergo just a much smaller scale transformation in order to reach a more stable state. So any nucleus that is in an unstable state is said to be radioactive. A radioactive nucleus which is also sometimes called a radionuclide, if you want to put it all in one word. So that's what we would call a nucleus that's not really stable. It has too much of either the protons or the neutrons, or maybe too much of both, and it's going to eject something. It's going to spit something out. So it's not always exclusively specific atoms. You might have heard, for example, elements like uranium are always radioactive, and that's true. But there are other elements like carbon, for example, that have both stable isotopes and not so stable isotopes. So carbon-12, atomic number 6, mass number 12, carbon-12 is stable. Carbon-12 is a stable isotope of carbon. Is a stable isotope. On the other hand, carbon-14 is not. Carbon-14 is what we would call a radioisotope. Carbon-14 is a radioisotope, which means it's radioactive, which means its nucleus is unstable, which means its nucleus wants to transform in some sort of way. Carbon-14 specifically undergoes a process known as transmutation, in which it turns into nitrogen. So I'll write out the nuclear equation here, and we'll explain what's going on with nuclear equations soon enough. But yeah, carbon-14 turns into, turns into nitrogen atomic number 7 by which process? Oh, I've already forgotten. Let's see, so it looks like it would be by beta emission, if I'm not mistaken, so it'll still be a mass number of 14, and it will eject an electron out of the nucleus, also known as a beta particle. If you don't understand what I just wrote, don't worry, we'll explain it in due time. So, yeah, this is how atoms of one element can transform into atoms of another element. This is a nuclear equation. It describes a process that occurs exclusively within the nucleus. Nuclear equations describe events that happen exclusively within the nucleus. So in this case, we would say that carbon-14 underwent what's called beta decay. It ejected an electron not from its orbitals. The electron came out of the nucleus of the carbon-14, and as a result turned into nitrogen-14, which is a stable element. Well, a stable isotope of the element nitrogen. Okay, so let's talk about all of the different particles that can be shoved into or ejected out of a radionuclide. A radioactive nucleus. Let me pull up the... there it is. Okay, so here's a list of particles, and by no means is this everything you'll see in a nuclear equation, but if you memorize these, you're pretty much good to go with most nuclear equations. First, you've got the alpha particle, which is essentially the nucleus of a helium atom. It's got a mass number of 4 and an atomic number of 2. And of course, it's basically just a helium atom minus the electrons, so it actually has a positive 2 charge. Let's see, anything else I need to say about alpha particles? Not really, but the alternative representation, as you can see in the symbols column, is just the Greek letter alpha. So whether you treat it as helium or you treat it as alpha particles, they're essentially the same. We don't really care much about the electrons outside the nucleus when it comes to nuclear equations, so if you're asking what about those, don't worry about them. Beta particles, also known as electrons, as you saw, I represented them as just an electron. No mass number. Electrons don't exist in the nucleus, at least not as electrons, so they don't contribute to the mass number. They have negligible mass in comparison to neutrons and protons. And they have an atomic number of -1, not because they're the negative first element, but because it'll make sense when we look at the math later. Atomic numbers don't necessarily mean what they have meant up to this point in the course. And of course, the alternative representation for the electron is just the Greek letter beta. let's see. Positrons are basically the opposite of an electron. Positrons are the antiparticle of an electron, and if you get into the really deep subatomic particle physics, which you probably won't see until you're in college, you'll learn more about these antiparticles. But yeah, that's the positron. It's the anti-electron. Protons can be represented as just protons, atomic number 1 and mass number 1, or as hydrogen, because, well, that shouldn't surprise you given everything we've done with acids and bases. We've been calling hydrogen ions protons, and yeah, so proton, hydrogen, same thing. Neutrons have an atomic number of 0 and a mass number of 1. And then you've got gamma radiation, which has no mass and no atomic number either. It doesn't affect the total number of protons in the nucleus, it's just energy. If the reason that your nucleus is unstable is because it has excess energy, it will just eject that excess energy in the form of gamma radiation. So those are the particles you're going to want to get to know. Make sure you memorize these. And for the symbols, make sure you memorize both versions for the ones that have 2 versions, because you never know what you're going to get. I do want to add on to this list deuterium and tritium. Sometimes you'll see these, maybe not, but deuterium and tritium. Deuterium and tritium are the isotopes of hydrogen. Deuterium and tritium. Deuterium and tritium. I don't know why I wrote my first T like that. So deuterium is a hydrogen atom that has a mass number of 2. It's got 1 proton and 1 neutron in its nucleus. Tritium, you can guess just from the tri in its name, is the 3rd isotope of hydrogen. It has a mass number of 3 while still maintaining an atomic number of 1. 1 proton, 2 neutrons. So those are 2 isotopes of hydrogen. Deuterium I see more often, and deuterium actually gets its own symbol. Deuterium can actually be represented with a capital D. So if you see a capital D and you're wondering what that is, that's deuterium. Sometimes when they do experiments with in order to, I don't know, keep track of a particular water molecule, they will actually use deuterium as one or both of the hydrogen atoms in that water molecule. So that would be given the symbol D2O rather than H2O. And I believe this is sometimes called heavy water. Heavy water. I'll double check that later. I forget if heavy water was the name for water using deuterium isotopes of hydrogen, or if it was just an alternative name for hydrogen peroxide. But I'll double check that, and if it needs correcting, I'll point it out in a pinned comment. If it's not pointed out in a pinned comment, you can assume that the name heavy water is accurate for D2O. But yeah, it's just H2O with 2 extra neutrons, 1 each for the 2 deuterium atoms. It's still hydrogen, it's just got 1 extra neutron each. Okay, and as for tritium, all I can say is that's the stuff that Dr. Otto Octavius wanted to obtain for his experiment in the second Spider-Man movie from the original trilogy with Tobey Maguire. I wonder how many of you are old enough to even remember that movie, or, well, You've probably seen it, who knows? Maybe you saw the more modern ones because, you know, they're more recent. I'm just rambling at this point. Let's move on. So, deuterium, tritium, you might see those occasionally, so know what they are in addition to that list. So, alpha, beta, positrons, protons, neutrons, gamma rays, and deuterium and tritium. Commit those to memory, and you will have a very, very easy time with this chapter. This chapter overall is pretty easy. There isn't a lot of heavy math. It's mostly whole number addition and subtraction. There will be a little bit of calculator work later, but most of the math is pretty simple. So let's talk about some of the different reactions that you can do with these particles. So here's another chart showing you different types of nuclear reactions. They're usually going to be in two categories. One where something is added to the nucleus, which is usually called capture or bombardment. And the other type is where things are ejected from the nucleus. That's what we call decay or radiation. So first type we see there is alpha decay, also known as alpha radiation, or alpha emission. That's another word that's sometimes used. So that's telling you that an alpha particle is coming out on the product side. So the nuclear equation column, I don't like the way that it's written. I think I'm going to rewrite these myself to clarify them. And I think the last one for electron capture is just wrong. But yeah, alpha decay, that's when an alpha particle is ejected out of the nucleus and comes out as one of the products. Beta decay is when a beta particle, in other words, an electron, comes out of the nucleus. Gamma decay is when you eject gamma radiation, and so on and so forth. Pretty simple, straightforward. Electron capture is that last row. That's where a beta particle is absorbed by the nucleus. So I don't know what they're doing there with the way they've written it, but let's go ahead and fix these, because even the ones that are right aren't really clear. I mean, they're clear to me because I know what they're supposed to say, but they might not be that clear to you. So alpha decay. So if you have something like, let me do a concrete example so that these are easy to understand. Let's do uranium 238. Uranium is element number 92, so that's its atomic number. And if you're wondering where I'm getting these, periodic table. As for mass number, I think 238 is one of the isotopes of uranium. If that number is wrong, well, that's okay, because the point isn't really to get the right number. The point is to show the process. So alpha decay or alpha emission from a uranium-238 nucleus would result in an alpha particle. Again, you can represent that with the Greek letter alpha or with just the symbol for helium, so that's going to be 2 and 4. And the other product is going to be whatever's left after ejecting an alpha particle from uranium. So the math is really simple here. Some of you might already have an idea as to what needs to be done. The atomic numbers on the left have to equal the atomic numbers on the right, and the mass numbers on the left have to equal the mass numbers on the right. So if this is an atomic number of 2, then that means we've got an atomic number of 90. 90 plus 2 is 92. And then 238 is equal to 4 plus 234. Okay. For element number 90, what is that? Element number 90 is thorium. Element number 90 is thorium. So when uranium undergoes alpha decay, it emits an alpha particle and turns into a thorium atom. Okay, next up we've got beta decay. Well, we've already shown an example of that, which is the beta decay of carbon. A beta particle, also known as an electron, comes out as a product. And yeah, 7 plus -1 is 6, so that's balanced. And then 14 is equal to 14 plus 0, so that's balanced. So there you go. You're good to go with that. Gamma decay. I mean, I guess typically what they'll do for gamma decay is they'll just give you something like let me think of a good element to use. Let's say, for example, phosphorus 30. Let's say you've got phosphorus 30. Sometimes they'll mark it with a star to indicate that it's in an excited state. It has excess energy. And then on the product side, you just rewrite the same thing because the atomic number and mass number of a gamma ray is 0. And there you go. Now you don't have the star. Essentially, that means you lost the energy. A better example that I can think of is what happens when two antiparticles collide. What happens when a positron, which is just an electron with a +1 atomic number, you can also call it a beta plus. You can also, you can also represent it like this. A positron collides with an electron. Or in other words, a beta plus collides with a beta minus. What is the end result? Well, 0 plus 0 is 0, and 1 plus -1 is also 0. So yeah, both of those particles disappear and they get replaced with energy. And of course, same result here. It's just representing the positron and electron using Greek letter beta. So yeah, this is what you might refer to as annihilation in physics. If you're not taking physics, don't worry about that. But yeah, this is annihilation. Let's see if I can spell it correctly. I think that's how you spell it. When two antiparticles collide with one another, they annihilate, they disappear and turn into pure energy. Okay, so that's two examples of gamma emission. Positron emission. So positron emission, let's say we did... what should I use? Let's do... Actually, what if we were to reverse... No, let's not do that. Maybe I should have prepared examples of these ahead of time. What would be a good positron emission example? You know what? Should I? Well, I do want to do... Okay, fine. This might not be realistic, but I'll just make something up here. Let's say that we have oxygen 14. Actually, no, oxygen 15. Let's say we've got oxygen 15, which is not the most stable of oxygen isotopes. So that's element number 8 with a mass number of 15, as opposed to the usual oxygen isotope with a mass number of 16. So this oxygen can undergo positron emission. It can eject a positron, so that's going to be one of the product particles. And then the other product will be what? Let's see, 8 is equal to 1 plus 7, and 15 is equal to 0 plus 15. Okay, so we would get nitrogen 15, which is probably not the most stable version of nitrogen, but it's probably more stable than oxygen. Maybe. I don't know. It's kind of hard to directly predict stability. Well, I'll give you some guidelines later that are useful in predicting stability, but you'll see that those guidelines themselves are, well, just that, guidelines. They're not rules. The only way to know for sure is to do the experiment in the lab, a safe, controlled lab that is, you know, well-regulated, not radioactive Boy Scout backyard labs. Please don't turn your neighborhood into a nuclear waste zone, because that's what the radioactive Boy Scout did. Anyway, moving on. We just finished a positron emission example, an electron capture example. Maybe I should do it with this oxygen 15 again. So with oxygen 15, let's do an Oh, actually, before I do that, I almost forgot. Positron emission, the way it works, the way that you generate positrons, and by the way, it's related to the way you generate electrons in the nucleus, is through the decay of protons or neutrons. So I remember when I was in maybe 5th grade and I had first learned about, you know, the subatomic particles, the electron, the proton, and the neutron, I thought to myself, well, if the electron has a negative charge and the proton has a positive charge and the neutron has a neutral charge, then maybe the neutron is really just a proton and an electron fused together. Well, turns out that is exactly the case. Because a neutron when an atom is undergoing beta decay, what's really happening in that atom is a neutron inside of its nucleus is converting into a proton plus an electron. It checks out. 1 is equal to 1 plus 0, and 0 is equal to 1 plus negative 1. So whenever you see a beta decay, like what was happening here with carbon 14 turning into nitrogen 14, one of the 8 neutrons, carbon 14 has 8 neutrons and 6 protons, one of those 8 neutrons turned into a proton and ejected an electron. So electron just gets ejected out, we actually see it, and then the new proton is still in the nucleus, and now you've got 7 protons and 7 neutrons as opposed to 6 and 8, which you had before. So that's what's really going on under the hood when it comes to beta decay. You probably don't need to know that, depending on how tough your teacher wants to be for this chapter. The other process for positron emission, it's the proton converting to a neutron. So a proton can also convert to a neutron by ejecting a positron. Again, the math checks out. 1 is equal to 1 plus 0, 1 is equal to 0 plus 1. It works. So yeah, that's what's really going on. That's where the electrons and positrons are coming from whenever you just see them being emitted out of a nucleus. That's how they're produced. Anyway, where was I before I went off on that tangent? Oh, right. We wanted to do an example of electron capture. Electron capture. I think I said I wanted to do it with oxygen 15 again, so let's go for that. So let's say we have oxygen 15 here, and we do an electron capture. So this time our particle is on the reactant side. Capture or bombardment happens on the reactant side. Let's see, 8 plus -1, that's going to be 7, so it looks like that's nitrogen. And then 15 plus 0 is 15. Oh, wait a minute. Positron emission and electron capture essentially lead to the same result. Positron emission and electron capture effectively lead to the same result. It's just that one process actually requires you to bombard the target nucleus with beta radiation, and the other process can happen without any external radiation needed. Okay, and those are some basic nuclear reactions. By the way, with electron capture, they show this in the chart. Electron capture is also associated with the ejection of X-rays, so you'll get X-ray photons coming out of it. And I guess an easy way to understand where that X-ray is coming from. Normally, when you want to eject electrons from an atom, you fire photons at it. And the closer those electrons are to the nucleus, the higher the frequency of the photon that's needed. More energy is required, which means you need a higher frequency photon. So visible light is probably not going to be high enough in frequency, which is why you need something stronger. Not even ultraviolet radiation, you're going all the way up to the X-ray category, because this electron that you're hypothetically trying to eject, of course we're not ejecting it, we're actually absorbing it, but if you were trying to eject an electron from the nucleus, that's super close to the nucleus because, well, it's in the nucleus. So, of course, you would need some really high frequency radiation to eject it, which means if you do the opposite process, your nucleus absorbs an electron, then you would expect it to eject high frequency radiation. So that's where that X-ray is coming from as an additional product. You probably don't even need to be aware of the fact that X-rays are emitted when electrons are captured, but just FYI, in case you have one of those instructors that actually cares about that. And yeah, aside from that, I think that pretty much covers all of the basic ones. There's bombardment with neutrons when you add a neutron to a nucleus. A neutron shows up on the product side, but they all follow the same pattern. Absorbing neutrons, ejecting neutrons, absorbing, I guess, deuterium or tritium, or ejecting them. It all pretty much works the same way. Make sure the numbers in the top add up on both sides of the equation, and make sure the numbers on the bottom are also adding up to the same thing on each side. And there you go. It's not that complicated. Okay, where do we go from here? So these nuclear reactions tend to happen with radioactive nuclides. And I guess I should define the difference between nuclei and nuclides. So this is something that I actually had to look up, because up until this point I had been using the terms interchangeably. Nuclei versus nuclides. What's the difference? It's a really subtle difference that most of you probably won't care about, but for the few who do care, nuclei A nucleus refers to, an individual nucleus of a particular atom, whereas a nuclide is just a class of nuclei that have the same number of protons and neutrons. So, for example, if I was talking about, let's say I had 3 atoms of tritium. Let's say I had 3 atoms of tritium. Let's say I had 3 atoms of tritium. Each of these would be a nucleus. I have 3 nuclei, but they all represent the same nuclide. They all represent the same number of protons and neutrons. In this case, 1 proton to 2 neutrons. I guess another easier way of understanding the term nucleus versus nuclide is if you compare it to atoms versus elements. If you compare it to atoms versus elements, it's pretty much the same kind of relationship. If I say I have 3 atoms of oxygen, for example, at the end of the day, all 3 of those atoms are 1 element. So atoms is to elements as nuclei is to nuclides. So there you go, for those who actually cared about the specific definition. That's what it is. I'll pretty much be using nucleus and nuclide interchangeably, but there you go for the people who really wanted to know. Where do I want to go from here? Let me check my notes. Oh, actually, let me list. There's one more process that you might hear of for nuclear equations, which is called transmutation. And really, some of these do count as transmutations if I'm not mistaken about the definition. A transmutation is basically any nuclear reaction in which, one atom of one element turns into another element. So the beta decay of carbon-14 into nitrogen-14, that would also be called a nuclear transmutation, if I'm understanding the definition correctly. If I'm not, then you know the deal. I'll correct myself in a pinned comment. Okay, predicting stability. Let's talk about predicting stability. Maybe I should do this on a new sheet. Yeah, let's do it on a new sheet. Predicting stability. Predicting stability of nuclides. As with all things in chemistry, these are guidelines, not rules. But there are some interesting patterns that we've noticed, and before I point them out, let me show you this graph. I don't know how clear it's going to be because I had to zoom it out a lot just to fit it on the screen. But what you see in front of you on the screen, on the vertical axis, you are plotting the number of neutrons in the nucleus, and the horizontal axis is the number of protons in the nucleus. So the blue spots on the graph are stable nuclei, and everything else is radioactive. So if you're in that blue range, then you are said to be within the band of stability, or the belt of stability. There's basically a range, and I guess this graph doesn't show it all too well. So let me just draw up my own graph here. Neutrons versus protons. You start off almost going up in a linear fashion, but eventually it starts to curve upward more and more and more over time. And yeah, you have this kind of range where if your nucleus is stable, then it's gonna be somewhere within this range. This range is called the band or belt of stability. Band or belt of stability. So all stable nuclei are going to be somewhere within here, but not necessarily everything that's within here is going to be stable. Okay, let's look at it again. Is there anything else I wanted to point out? I don't think so. Oh, and they've drawn that black line. So that black line is where you would think the band of stability would be based on the first few elements. Because the first few elements, elements 1 through 20, you notice that the neutron to proton ratio is roughly 1 to 1. There's approximately 1 neutron for every 1 proton. So if that pattern had continued, then your stable nuclei would have fallen along that black line, but of course you see that that's not really the case. So let's talk about a bunch of different, I guess you could call them sub-ranges of stability. Let's talk about neutron to proton ratios. Neutron to proton ratios. So 1 to 1. 1 to 1 is a stable neutron to proton ratio for elements 1 through 20. Elements 1 through 20, roughly they have an equal number of neutrons to protons if they're stable. Then from elements 21 through 40, and these I don't expect you to memorize them. You can just look them up in a book whenever needed. But elements 21 through 40 appear to need more neutrons. So you need 1.25 neutrons per proton, or in other words, 5 neutrons for every 4 protons. Then when you get into the 41 to 50 range, elements 41 through 50, those require approximately 1.4 neutrons for every 1 proton, or in other words, 14 neutrons for every 10 protons. Then you get to a 1.5 to 1 ratio for elements 51 through 83, I think it was. Yeah, 83. And then for elements 84 and above, they're pretty much all unstable. So anything, wait, did I do that right? No, other way. Greater than, or anything greater than or equal to 84. Anything greater than or equal to 84 in atomic number is pretty much guaranteed to be radioactive. So yeah, there you go. So you can have 2 different types of problems for elements 1 through 83. You could have too many neutrons, or you could have too many protons. Or alternatively, you can say too few neutrons, which is the same as having too many protons. So those are 2 typical problems that you can have for those first 83 elements. And based on that, you can actually predict what type of decay those radioisotopes are going to undergo. Again, you don't really need to know this unless you have one of those teachers. I feel like I've been saying that way too many times. And I'll probably say it more times in this video. Where was I? Right, so what if I have too many neutrons? So if I'm, let's see, too many neutrons and too few protons would mean you're above the belt of stability. So here, too many neutrons, and if you're below the belt of stability, then that's going to be too many protons. And of course, you don't need to look at the graph to see where it is. You can just use these ratios, which is what I'm going to do, because looking at a graph to see whether or not your specific nuclide is on that blue staircase thing that I had up on the screen earlier, trying to figure those out with pinpoint accuracy, it's too much of a chore. I mean, it's doable, but it's just too much. It's easier to just look at the neutron to proton ratios. So if you have too many neutrons, then you need to reduce the number of neutrons and increase the number of protons. So what would you do? If you have too many neutrons, if you're above the belt of stability, then what you would try to do is undergo beta decay. You would undergo beta decay. Why? Because we already saw the underlying process for beta decay requires a neutron to split up into a proton and an electron. So if you have too many neutrons, you lose a neutron, you gain a proton, and of course you eject an electron. That helps reduce your problem. And maybe you'll have to undergo beta decay multiple times. Maybe you have to convert multiple neutrons into protons, but that would be the way to go. So that would shift you to the right on this graph, if I'm not mistaken. Yeah, if you were outside here because you had too many neutrons, then, well, it would shift you down and right. It would shift you down because you're losing a neutron, and it would shift you right because you're gaining a proton. So effectively, it moves you diagonally down and to the right if you're above the belt of stability. On the other hand, if you have too many protons, if you're below the belt, too many protons, then you would want to undergo the other process. You would want to undergo positron emission or electron capture. Positron emission or electron capture. We already showed earlier that positron emission and electron capture are the same thing. We did the example of positron emission for oxygen-15 and electron capture for oxygen-15. Both resulted in nitrogen-15. So both processes achieve the same thing essentially, but let's say it's positron emission. For positron emission, in order to generate a positron, a proton needs to turn into a neutron. So basically the reverse of what beta decay does. Decreases the protons, which moves you to the left. So if I had something below the belt of stability, like here, positron emission would cost one proton, moving you one step to the left, and would produce one neutron, moving you one step up, effectively moving you diagonally to the upper left direction. And there you go. So that's if you're above or below the belt of stability. What about elements greater than or equal to 84 in their atomic numbers? Well, those have both problems. They have too many protons and too many neutrons. At that point, you've got so many protons that no amount of neutrons is going to provide enough cushioning to support the strong nuclear force in keeping it all together. They might last for a while, but eventually they're going to decay. So those bigger atoms, they're going to have to shrink down. They're going to have to convert into smaller elements eventually. And the fastest way to get rid of protons and neutrons at the same time, the fastest way to get rid of both at the same time is through alpha decay. An alpha particle contains 2 protons and 2 neutrons, so you would lose an equal amount of both. So as far as this graph is concerned, elements 84 and above don't even make it onto the graph, but if they did make it onto the graph, they would be in this upper right corner. And what alpha decay does is it reduces your neutrons and it reduces your protons. So effectively, it moves you diagonally down and to the left. So something from outside of the graph can eventually, through several alpha decays, gradually inch its way towards the upper right corner of this graph. And then once you get close, maybe you land in the belt of stability, maybe you're too far, maybe you're still too far above or too far below, in which case beta decays or positron emissions, one or the other, whatever is needed to get it into the stable zone, or at least the relatively stable zone. So yeah, that's predicting stability of nuclides, and then based on that, predicting what kind of decay they would undergo if they need to decay at all. What's one more thing that I need to mention? Oh, right. So another thing, well, 2 other things that are worth noting for predicting stability. It turns out that having even numbers of protons and neutrons seems to increase stability. Even versus odd neutron and proton counts. Even versus odd neutrons and protons. So, of all the stable isotopes of the known elements, it turns out that an overwhelming majority of them have an even number of neutrons and an even number of protons. Some of the stable nuclides have just an even number of neutrons with an odd number of protons, or an even number of protons with an odd number of neutrons, and very, very few of the stable nuclides have both odd neutrons and odd protons. So it seems that having an even number, for whatever reason, increases stability. Just an interesting pattern that chemists have noticed. Another interesting pattern that chemists have noticed is the following numbers seem to increase stability. The following numbers seem to be what's the word I'm looking for? They seem to have the secret of stability contained within them. That's really the best way I can put it, but wait till you hear what chemists call these numbers if you think that's too cheesy. Just wait until you hear what chemists call these numbers. So these numbers are 2, 8, 20, 28, 50, 82, and 126. So radionuclides, well, they wouldn't be radionuclides if they're stable. Nuclides that have 2 protons or 2 neutrons, or better yet, 2 of both, are particularly stable. Having 8 neutrons or protons, 20 neutrons or protons, 28, 50, 82, or 126 neutrons, not 126 protons. And the simple reason for why protons are excluded for 126 is because we don't have 126 elements. We only have 118 so far, and there's no telling whether or not we're going to be continuing past 118 elements. But I would imagine, based on this pattern, that if we did discover a 126th element, that it would probably be stable if this pattern actually holds. So these numbers, you won't believe what chemists call them. Are you ready for this? These are called magic numbers. I did not stutter. Scientists call these magic numbers. Magic. That's how you know that they just gave up on trying to find an explanation. Magic numbers. You probably don't need to memorize these unless, again, for maybe this is the 5th time I've said it so far, unless you have one of those teachers. You probably don't need to memorize the magic numbers, but, you know, just knowing about them is good enough for me. Okay, I think we're ready to do some problems. Yeah, let's go ahead and do some problems. Oh, actually, before that, I should have mentioned this when we were talking about atomic numbers 84 and higher. So these elements, uranium is the example that comes to mind for me. They will often need to undergo multiple alpha decays in order to, eventually turn into something stable, something that falls within the band of stability. So they follow a very, I wouldn't say predictable, that's not the right word. They follow the same sequence of decays every single time if it's the same starting nuclide. If you start with a particular nuclide, every single time that a nucleus from that family decays, if it's from an element numbered 84 or above, it will actually follow a specific sequence of decays and, convert into the same elements at the same steps every single time. This is what's known as a radioactive series or a radioactive decay series. And here is an example of that. So the decay of uranium-238. It always starts by converting into thorium-234. Then it undergoes 2 beta decays, turning into uranium-234, then turns into thorium-230, then radium, and so on and so forth. You can follow the arrows, and eventually it ends up converting into lead. I believe that says 206. It's a bit too tiny for me to read. But yeah, that's an example of a radioactive decay series, which is not the same thing as a chain reaction. We will talk about chain reactions later. But this is not a chain reaction, it's a decay series. Make sure you don't confuse those two concepts. Okay, now let's go ahead and look at some problems. Where did I put them? There we go. These first few I don't think I need to cover. Write the following isotopes in hyphenated form. So for example, carbon-14. We saw this way back in, I think, video number 3. If you don't remember how to do this, it shouldn't be too hard to go back and review it real quick. It's super easy. It's the name of the element, hyphen, and then the mass number. You don't need the atomic number because the name of the element gives it away. You can just look it up on the periodic table. So yeah, that first one is sodium 24, aluminum 29, and so on and so forth. Number 2 is basically the reverse of number 1, so you know how to do that. Number 3, for the following isotopes that have missing information, fill in the missing information to complete the notation. Okay, so X represents the missing information, so yeah, you know what to do here. If you know the atomic number, then you can look up the element symbol on the periodic table and vice versa. So yeah, that's easy enough. I'm not going to go through that. Number 4, for each of the isotopes in exercise 21.1. Oh, okay, so the first problem. Determine the numbers of protons, neutrons, and electrons in a neutral atom. Yeah, we're not doing that. That's beginner stuff. By this point, this shouldn't be giving you any trouble at all. Okay, and I think this is also going to be a bunch of skippables. Number 5, write the note. Yeah, we're skipping that. Number 6, calculate the density of the magnesium 24 nucleus in grams per milliliter, given that its diameter is 1 × 10⁻13 centimeters and is spherical in shape. So if you remember your geometry and the volume formula for a sphere, you should be good to go with that. Take the mass, divide it by the volume, and you're good to go. 7, we've got, what are the 2 principal differences between nuclear reactions and ordinary chemical changes? Okay, well, one difference I can think of off the top of my head is what I said earlier. Nuclear equations reflect things that are going on in the nucleus of the atoms involved. It has nothing to do with the electrons orbiting outside the nucleus. So that's one difference. What else? What's another principal difference between nuclear reactions and ordinary chemical changes? I'm not really sure what else they're looking for. Oh well, I'll look at their answer key later and mention the second thing in a pinned comment if I can find it, if it's even in their answer key. Number 8, the mass of sodium 23 is... Oh, yeah, we'll cover this later. This is about mass defect, which we haven't talked about. We'll go back to that. Skipping number 8 temporarily. Number 9, which of the following nuclei lie within the band of stability shown in the figure? So what they want you to do is go to the figure and actually find the coordinates, but we're not going to do that. We're just going to go based on neutron to proton ratios. So chlorine 37. Let's see. Chlorine is element number 17. So that means we've got 17 protons, and out of 37 total nucleons, that means you've got 20 neutrons. So 20 neutrons, 17 protons, that's a little above a 1-to-1 ratio. And since it's atomic number 17, we said elements 1 through 20 are going to be typically a 1-to-1 neutron to proton ratio. So yeah, that doesn't look very 1-to-1 to me. If it was like 18 neutrons to 17 protons, I'd say you would get away with it, but 20 to 17, that's kind of overkill. So I would say that that's above the band of stability. Calcium 40, that I think is a perfect 1-to-1 actually, because calcium is element number 20, so 20 protons and 20 neutrons. Yeah, it's 1-to-1. It's perfect. Bismuth 204. Bismuth is element number 83. Ooh, barely in there. Element 83. So 204 minus 83. Let's see. 204 minus 83 is 121, right? Yeah, because 200 minus 80 is 120, and then 4 minus 3. Yeah, it's 121. Okay, so we've got 121 versus 83. If it was 120 to 80, that would be a perfect 1.5 to 1. 121 to 83, I mean, it's close enough. Well, no, it's still not good enough. 3 additional protons above 80 would require about 4 or 5 extra neutrons, which we don't have. We only have 1 extra neutron above 120. Okay, so not enough neutrons. That would be below the belt of stability, is what I would expect. And yeah, you can carry on with this process for the rest of those. I think I've shown you essentially how to do it. And then again, you're probably not going to be asked a question like this in the first place. Typically, based on the homework I've seen from my chemistry students, they never ask this sort of thing unless they're trying to be extra challenging. Number 10, which of the following nuclei lie within... Okay, so it's the same thing. Let's move on. Write a brief description or definition of each of the following. I think we've done a good job defining all of those, so we'll skip number 11, but make sure you know how to define those things. If you're struggling to come up with the words, then maybe you don't know them as well as you think you do. It's easy to brush this off and say, I know what these are, but when you're forced to put pen to paper, can you give a description that one of your peers would be able to understand at the very least, if not members of the general public who may not even know much science? It's good to work on those communication skills. Anyway, number 12. Which of the various particles that may be produced in a nuclear reaction are actually nuclei? Oh. Okay, well, the beta particle is not. The positron is not a nucleus. Alpha particles are nuclei. They are the nuclei of helium atoms. So that's one. Protons are nuclei. They are the nuclei of hydrogen atoms. Anything else? I think that's it. Neutrons alone can't be nuclei. You need to have at least one proton. Okay, so that was an interesting question. 13. Complete each of the following equations by adding the missing species. You've seen enough examples at this point that you should know how to do this. Make the numbers in the bottoms, add up on both sides. Make the numbers in the tops, add up on both sides. Let's just do one example here. Let's do Oh, let's just do that first one. Oh, actually, no, not the first one. Let's do the fourth one. Let's do part D, because that one can throw some people off, so let's make sure we know how to do that. Okay, change of plans. Let's see. So it was uranium-235. Which decays into 3 different things. Some unknown. We'll just leave some space open for that. Plus cesium-135, it looks like. Cesium-135. Plus 4 neutrons. Most of you are probably not going to be taken aback by this, but for those that are a bit confused by this, you don't necessarily have to eject one of every subatomic particle. Sometimes you have multiple neutrons or multiple positrons or beta particles coming out of nuclei or going into them. Okay, so 235 minus 135 is 100. And then you're also going to subtract 4 times 1, so that's 100 minus 4 is 96. And then we've got 92 minus 55 and also minus 4 times 0. So 92 minus 55, 92 minus 50 is 42, and then minus another 5 is 37. If my math is right, let me double check. 42, 37, yeah. Okay, and element number 37 is rubidium. Element number 37 is rubidium. So this is rubidium 96. All right, that takes care of that. You know how to do the rest. 14 looks like more of the same. Complete the equation. Really easy stuff. It shouldn't be giving you too much trouble. This stuff is so easy that I've tutored students who were just taking a regular chemistry course, and this was something they were doing in the 3rd or 4th week of their class. That's how easy it is. But of course, you don't need me to tell you that. You've just been through equilibrium. It doesn't get harder than that. Okay. Do I want to keep going? Yes, more problems. Let's see what else we've got. Write a balanced equation for each of the following nuclear reactions. The production of oxygen-17 from nitrogen-14 by alpha particle bombardment. Okay, so basically the same as those 2 previous problems. But here you want to go from a written description to write the name. What am I saying? To write the equation, not the name. Brain malfunctions. Okay, so the production of oxygen-17, so that means it's on the product side. Oxygen is atomic number 8. You can look it up on the periodic table if you don't know it by heart. From nitrogen-14, so nitrogen is atomic number 7. Mass number 14 in this case. By alpha particle bombardment. So the alpha particle is a reactant. Okay, and do we have an extra product or an extra reactant here? 2 plus 7 is 9, so yeah, we definitely have something else here. 14 plus 4 is 18, 17, so that's a 1. So that's a proton or a hydrogen atom if you prefer. You can represent it either way. Okay, there we go. Something I didn't mention, and maybe this is a good opportunity to mention it, you might see some shorthand notation for simple nuclear equations where, it's just one of each particle. You could represent this reaction right here in the following way. You could summarize it as, let me see if I've got this right. So it would be nitrogen 14, and then on the reactant side you have an alpha, on the product side you've got a proton, and then of course you've got oxygen. Let me double check and make sure that I've got this right, because I rarely see this notation, but I have seen it every now and then, so just in case you run into it, I want to make sure I'm doing this right. Let me look through my book real quick. Okay, it doesn't appear to be in this book. I know I've seen it somewhere, and I'm pretty sure it was in one of my books. Oh, there it is. Okay, yeah, found it. Oh, the exact one that we actually have here. Yeah, the only difference between what's in the book and what I wrote is that they actually listed the atomic numbers. And, well, I guess I did that for oxygen, but not for nitrogen. So yeah, this shorthand notation, if you see it, the thing before the comma is on the reactant side, the thing after the comma is on the product side, and that's basically it. So if you see it, that's what it means. Don't be too taken aback by it. Okay, and I think with that one example, we can skip on the other three. You can do them on your own. Number 16, technetium-99 is prepared from molybdenum-98, which combines with a neutron to give molybdenum-99, an unstable isotope that emits a beta particle to yield an excited form of technetium-99. Represented as technetium-99 with a star. There's that star thing again. I told you about it earlier, and I guess they're just going to straight out tell you. This excited nucleus relaxes to the ground state, represented as technetium-99 without the star, by emitting a gamma ray. The ground state of technetium-99 then emits a beta particle. Write the equation for each of these nuclear reactions. Okay, so pretty much the same as 15, but it's a sequence of steps. Radioactive series, if you will. 17, the mass of... Oh, this is kind of like the one we skipped earlier, number 8. We'll go back to this. We haven't talked about mass defect yet. Number 18, for this reaction, if 100 grams of carbon reacts, what volume of nitrogen gas is produced at 273 kelvins in 1 atmosphere? I mean, at that point, it's just simple stoichiometry. So you could have done this with no knowledge of nuclear chemistry whatsoever. Convert your grams of carbon to moles of carbon. 1 mole of carbon is equivalent to 1 mole of nitrogen according to that equation. Convert your moles of nitrogen to liters of nitrogen. using the molar volume at STP, because 273 kelvins in 1 atmosphere, that is STP, 22.4 liters per mole would be the volume under those conditions for any ideal gas. Okay, so 18, not really the most relevant to this chapter. Let's move on. What are the types of radiation emitted by the nuclei of radioactive elements? We've been over them. Go back to that first chart that I put up on screen. Number 20, what changes occur to the atomic number and mass of a nucleus during each of the following decay scenarios? Okay, that you can keep track of on your own. Just calculate the change in the mass number and the atomic number and you're good to go. If you're gaining or losing protons, that's a change in your atomic number. If you're, well, it's a change in your atomic number and your mass number. And if you're gaining or losing neutrons, then that's a change in just your mass number. Unless, of course, what's going on is neutrons and protons are converting into one another, in which case your mass number isn't changing, but your atomic number is. So yeah, I think you can handle that on your own. 21. What is the change in the nucleus that results from the following decay scenarios? Yeah, you can do that on your own as well. I guess, yeah, A and B, I already showed you the conversion of a neutron into a proton and a beta particle, and the conversion of a proton into a neutron and a positron. Part C, capture of an electron, I didn't show you that, but I imagine you can figure it out on your own. Proton plus captured electron equals neutron. You can write out the equation and check that the math does work out. 22. Many nuclides with atomic numbers greater than 83 decay by processes such as electron emission. Explain the observation that the emissions from these unstable nuclides also normally include alpha particles. We already answered that. It's because you've got too many of both the protons and the neutrons, and the quickest way to lower both of those numbers is to eject alpha particles. 23. Why is electron capture accompanied by the emission of an X-ray? We explained that. 24. Explain in terms of figure 2. I don't even know if I... Oh, that was the graph with the belt of stability. Explain in terms of the graph how unstable heavy nuclides may decompose to form nuclides of greater stability if they're below the band, above the band. We already described that. 25. Which of the following is most likely to decay by positron emission? Explain your choice. It's going to be based on whether it's below the band or above the band. You can figure it out based on neutron to proton ratios and what they should be closest to based on the atomic number. So just based on these. Been there, done that. I'm pretty sure I went through an example of that. Well, I went through an example where we used these to predict whether or not it's unstable and whether it had too many neutrons or too many protons. But from there, the rest is easy because you already know where to go. That's the thing with this easy chapter. It's easy enough that there's not much for me to cover. Let's see, that was 25. Let's take a look at this set. The following nuclei do not lie in the band of stability. How would they be expected to decay? So again, look at their neutron to proton ratios. versus what they ought to be in order to be stable. And from there, predict whether they're going to undergo beta decay or positron emission or alpha decay. And of course, if you don't like positron emission, electron capture is an equivalent process. Okay, so 26, 27 is basically the same thing. Yeah, you know how to do these. It's just a matter of practicing them. Okay, and I think after this set of problems, we'll be ready to talk about some more topics. 28, predict by what modes of spontaneous radioactive decay each of the following unstable isotopes might proceed. We already know it's the same as 26 and 27. We already know how to look at neutron to proton ratios and make an educated guess about stability and whether it's too many neutrons or too many protons or just the right amount of each. And from there we know what type of decay is needed to get back to stability if it's unstable. 29. Write a nuclear reaction for each step in the formation of polonium-218 from uranium-238, which proceeds by a series of decay reactions involving the stepwise emission of alpha, then beta, then another beta, then 3 more alpha particles in that order. So yeah, you just want to write, let's see, 6 nuclear equations. Shouldn't be too hard to do. It's just kind of a chore because it's 6 of them. But you know, if you need the practice, that's 6 equations you can practice with. Number 30, write a nuclear reaction for each step in the formation of lead-208 from thorium-228, which, okay, so basically the same as 29. 31, define the term half-life and illustrate it with an example. So we've talked about half-life before. Let's go ahead and dig into the topic of half-life in the context of nuclear chemistry. We've done it before in video number 12 when talking about chemical kinetics. And in the chemical kinetics video, we did see some problems that involved radioactive decay. We did see that, but I skipped on them because I felt that it wasn't appropriate to dig into radioactivity at the time. So you might remember from video number 12 that for first order processes, for a first order process, for a first order reaction, half-life is constant. So the amount of time it takes to get from 100% to 50% equals the amount of time it takes to get from 50% to 25% equals the time to get from 25% to 12.5% and so on. For a first order process, the half-life is constant. You might also remember from the chemical kinetics video that a first order process is one whose rate determining step is unimolecular. Rate determining step in its reaction mechanism is unimolecular. Unimolecular. That is, there is only one reactant in the slowest step in its reaction mechanism. It doesn't need to collide with something else in that slowest step. Okay, well, just based on that description alone, we can easily see why all nuclear decays are first order. All nuclear decays are first order. All nuclear decays are first order because a radionuclide doesn't need any sort of external particles to run into it. That's not a decay process. That would be bombardment or capture, as we call it. All nuclear decays are first order because the only thing you need to decay is one nucleus that's not stable. If it's an unstable nucleus, it can decay all on its own. It can eject whatever particles it needs to eject, and it doesn't need outside assistance. All nuclear decays are therefore unimolecular. You don't have to interact with any other particles from the outside. All nuclear decays are unimolecular, therefore first order. Therefore first order. Therefore constant in their half-life. All right, so now that we've got that out of the way, we can relax. We don't have to worry about successive half-lives being shorter or longer. So, let me think here. Well, I guess we can write out the exponential equation that we typically use when dealing with half-life. We say that the final amount of particles equals the initial amount, n0, times e to the negative, I think the symbol they use is lambda, times time. Wait, no. This is the physics version of it. Let's see. The version that we used was something more like final amount equals initial amount times 1/2 raised to the total time divided by the half-life. Okay, so I guess you can use either of those two versions. If you're good with your logarithms and exponentials, then you should be comfortable using either of these. Had my wires crossed there for a minute. But if you look at this equation, and again, this is just FYI stuff, you don't really need to know it, that value lambda is typically going to come out in, let's assume that t is in seconds, then this value lambda, the rate of decay, is going to come out in units of what we call disintegrations per second. Disintegrations per second. Disintegrations per second. And we define one disintegration per second. One disintegration per second. We define that as a unit known as the becquerel, BQ. Again, not something you really need to know, but FYI stuff. And I'm not entirely sure why this number is special, but there's another unit that's used for decay rates, which is the Curie, named after Marie Curie, of course. The Curie, represented as Ci, is equal to 3.7 times 10 to the 10 disintegrations per second, or in other words, 3.7 times 10 to the 10 becquerels. I'm not sure why this number is particularly special, but I would imagine that it's probably the decay rate of a very popular radioactive nucleus. Maybe it's the decay rate for uranium. I don't know. Maybe I'll look it up and post what I find in a comment, or maybe I won't. But yeah, we've done half-life before. I don't think we need to review how to use this equation. If you need a review, you can go back to video number 12 and skip to the part where we were doing half-life stuff. But I'm just going to move on. We'll do an example or two as a refresher. So, how is half-life useful in the context of nuclear chemistry? Well, you can use half-life to figure out how old things are, specifically things that are super, super old, like fossils and stuff. That's typically done using carbon-14. So, using the half-life of carbon-14 to figure out the ages of fossils and stones and stuff, that's what's called carbon dating. It's based on the half-life of carbon-14. Carbon-14 has a half-life of, let me see if I copied this down. Yes, I did. 5,715 years. 5,715 years is the half-life of carbon-14. And I think the reason I copied that down is because eventually we're going to run into a question where they ask us to do a carbon dating problem, but they don't actually give us the half-life, interestingly enough. I don't know what else to say. I mean, aside from repeating stuff that we already said in video number 12, let's just move on and do some problems. Let's go back to the problem that actually sent us on this detour. 31, we should already know the definition of half-life by now. If you start with 100 grams of something with a half-life of, let's say, 2 minutes, then in 2 minutes you go from 100 grams to 50 grams. 2 more minutes you go from 50 to 25, and so on and so forth. It's the amount of time it takes to cut down the amount of a substance in half. 32. 1.0 times 10 to the negative 6 gram sample of nobelium has a half-life of 55 seconds after it is formed. What is the percentage of nobelium-254 remaining at the following times? 5 minutes after it forms, 1 hour after it forms. Okay, well, if they're looking for a percentage, then you don't actually need to know the starting amount. If you're looking for a percentage, you don't need to know the starting amount. And we'll illustrate that right here. So we've got 5 minutes after it forms, so you've got the final amount equals the initial amount times 1/2 to the total time, which is 5 minutes, over the half-life, which is 55 seconds. Convert the minutes to seconds. 5 minutes, or 5.0 minutes as they've written it, is going to be 300 seconds. 5 times 60? Yeah. 300 seconds, or 3.0 times 10 to the 2, to signify that it has 2 sig figs. But yeah, 300 over 55. So n over n0, the final amount over the initial amount, is equal to 1/2 to the 300 over 55. And then if you want to convert that to a percent, multiply it by 100%. And there you go. So the percent remaining is the amount remaining over the initial amount times 100% equals 1/2 to the 300 over 55 times 100%. Plug it all in. We've got 1/2, whoops, parentheses first, 1/2 to the 300 over 55. Well, technically I should do 300 over 55 first. But I'm going to take some liberties here with my sig fig rules. So it looks like we're getting about 2.3% remaining. And was that what they were asking for, the percent remaining or the percent decayed? No, they were asking what's the percent remaining. Okay, and 1 hour after it forms, repeat the same process, except instead of 300 seconds, 1 hour is going to be 3,600 seconds. I don't think you need to see me do that. Let's move on. Let's see, I believe that's plutonium-239 is a nuclear waste byproduct with a half-life of 24,000 years. What fraction of the plutonium-239 present today will be present in 1,000 years? Well, more than half of it, because it takes 24,000 years to lose half. 1,000 years is not enough to lose half. Not even close. But yeah, just apply the same equation. And in this case, they want the fraction, not the percent. So same process as I did here, except without the times 100% thing. So I guess I'll set it up. So half-life is 24,000 years, and the amount of time passed is 1,000. So n over n0 is what you're solving for, equals 1/2 raised to the 1,000 over 24,000. There, all good to go. The isotope Thallium-208 undergoes beta decay with a half-life of 3.1 minutes. What isotope is produced by the decay? So easy enough, just write the nuclear equation. Part B, how long will it take for 99.0% of a sample of pure Thallium-208 to decay? Okay, so pretty simple stuff. 99% decayed means 1% remaining. Be careful about that. But otherwise, it's pretty much the same thing we did up here. So we can say n over n0 times 100% is equal to 1.0%. 1.0% is equal to 1/2 to the, what did they give us? They gave us a half-life of 3.1 minutes, so what's unknown is the amount of time that passed, t over 3.1. Remember, this is in minutes, so the t that you solve for will itself be in minutes, times 100% there. And yeah, 1.0 divided by 100% is 0.010. I guess we would have to do logarithms. Okay, let's work this one out. 0.010 equals 1/2 to the t over 3.1. If we take the natural log on both sides, then we get natural log of 0.010 equals natural log of 1/2 to the t over 3.1. And the rules of logarithms allow me to bring the exponent to the outside, so that becomes natural log of 0.010 equals t over 3.1 times the natural log of 1/2. Okay, natural log of 0.010 over natural log of 1/2 and times 3.1. We've got 2 sig figs there, which means we're going to need 2 decimal places. That's exact, so I guess infinite decimal places. Okay, natural log of 0.010 is negative 4.61. So we've got negative 4.61. Multiply it by 3.1 and divide it by natural log of 1/2, and that will give you t. Okay, negative 4.61 times 3.1 is negative 1.4, or no, negative 14 I should say. Negative 14, and then negative 14 over natural log of 1/2, negative 14 over natural log of 1/2, rounded to 2 sig figs is 20. Is equal to 20, and that's in minutes. 20 minutes, 2 sig figs, that's why I'm including a decimal point after the 0. Okay, there we go. So it takes 20 minutes to decay 99% of it. Part C of problem 34, what percentage of a sample of pure thallium 208 remains undecayed after 1 hour? Okay, that one's easy enough to do. We've done examples of that before. Don't forget to convert the hour to minutes since your half-life is in minutes. And the rest is history. 35. Let's see, 1 gram of radium-226 produces 1/10,000th of a milliliter of the gas radon-222 at STP in 24 hours. What is the half-life of radium in years? Okay, so I would convert the volume of the gas at STP to moles using molar volume and multiply that by the molar mass to get grams. Actually, no, I would keep it in moles, and then I would convert the 1 gram of radium, figure out how many moles of radium that is. Wait, does that sound right? Let me think about this. Yeah, calculate the moles of radon produced using molar volume of an ideal gas. That would be equal to the number of moles of radium consumed. Convert that to grams of radium consumed. And that would leave you with grams of radium remaining. Once you've got your grams of radium remaining, divide it by the starting 1.000 grams of radium. And that gives you the fraction remaining. That would give you your n over n0. And set that equal to 1/2 to the t over half-life, and they already told you that t is 24 hours, so all that's left is to solve for the half-life. Okay, and that would involve using logarithm properties, but you've already seen how that goes, so nothing too different from... Once you get to that point, it's nothing too different from what we did here. Only difference is that instead of your unknown being in the numerator, your unknown is going to be in the denominator. That's pretty much it. So once you've got the stoichiometry parts out of the way, the rest pretty much follows from what we did here. Except you would start here at a fraction instead of at a percentage. I mean, you could calculate it as a percentage, but you're going to have to convert it to a fraction anyway. Yeah, I think those of you who've been on top of their math aren't going to have too much trouble there. Although, to be fair, they usually don't ask anything on this level of complexity either. Not that it's that complicated, you just have to sit down and think about it for a few minutes. But yeah, typically they don't ask questions that are this demanding in this chapter. All the more preparation for you, I guess. Number 36, we've got strontium-90 is one of the extremely hazardous species in the residues from nuclear power generation. The strontium in a 0.5 gram sample diminishes to 0.393 grams in 10 years. Calculate the half-life. Okay, so basically an easier version of 35 because you've got less steps to do. They've already got the grams remaining calculated for you. Grams remaining over the initial 0.500 grams equals 1/2 to the 10.0 years over the half-life. Use your logarithms and solve. Easy enough. 37. Is it more of the same? Calculate the rate constant for the decay. The rate constant. Let me see. So it would be... The rate constant, so that would be using the other version of the equation that I listed earlier. Where did I? Yeah, this right here. So maybe I should have called it, yeah, let me just rewrite it here. It's going to be n final equals n initial times e to the negative k for the rate constant times t. So let's see what it said. Calculate the rate constant for the decay of technetium-99 if it has a half-life of 6 hours. Okay, if it has a half-life of 6 hours, then when t equals 6 hours, n over n0 is 1/2. n over n0 equals 1/2 equals e to the negative k times 6.0 hours. And yeah, natural log both sides. Natural log of 1/2 equals natural log of e to anything just cancels the e, so equals negative k times 6.0. And I guess if you remember the shortcut formula, rate constant equals natural log of 1/2 divided by negative half-life. Yeah. But from here it's simple division. Natural log of 1/2 divided by negative 6.0. That will give you the rate constant in, I guess, disintegrations per hour. Okay. 38. What is the age of mummified primate skin that contains 8.25% of the original quantity of carbon-14? Yeah, this was the one. I saw this when I was preparing for this recording, and I thought they didn't mention the half-life of carbon-14. So if you want to solve it, it's not too different from any of the other problems we saw before it. Just note that the half-life of carbon-14 is 5,715 years. And there you go. Have fun discovering the age of that mummified primate skin. 39. A sample of rock was found to contain rubidium and strontium. Calculate the age of... Yeah, okay, yeah, we've done this stuff. 40. A lab investigation shows that a sample of uranium ore contains 5.37 milligrams of uranium-238 and 2.52 milligrams of lead-206. Calculate the age of the ore. The half-life of uranium-238 is 4.5 times 10 to the 9 years. Okay, so basically what they're saying is that it was initially all uranium. It used to be all uranium, but some of it ultimately converted to lead. And based on the amount of lead, how much uranium was it that converted into that lead? So similar to problem 35, where you need to calculate the moles of lead, and from there get the moles of uranium, and from there get the grams of uranium that were converted into lead. Add that to the 5.37 milligrams of uranium that are available at present, and that gives you the total amount of uranium for the past. And then from there, I think you already know what to do, so I'm not going to repeat those same instructions again. Let's move on. '41, plutonium was detected in trace amounts in natural uranium deposits by Glenn Seaborg and his associates in 1941. They proposed that the source of this plutonium was the capture of neutrons by uranium nuclei. Why is this plutonium not likely to have been trapped at the time the solar system formed 4.7 times 10 to the 9 years ago? So if you go back to, I think it was the previous page. Yeah, right at the top. The half-life of plutonium is 24,000 years, which is a lot, but the age of the solar system is way, way bigger than that. The age of the solar system is 4.7 billion years. So if you calculate how many half-lives that would have been for plutonium, 4.7 billion divided by 24,000, I mean, a billion divided by 1,000 is already a million. So if you have 1 million half-lives pass by, then I'm pretty sure that's enough time to get all of the plutonium to disintegrate. If you cut something in 500,000 times, there's practically none of it left, because eventually you'll be down to 2 atoms, and then you'll be down to 1 atom 24,000 years later, and then 24,000 years after that, well, you've only got 1 atom left, so it just disappears, converts into smaller atoms, or breaks up into other smaller particles, whatever it does. So yeah, even without doing the exact math, it's pretty reasonable to assume that after over 1 million half-lives, well, in the ballpark of 1 million half-lives, if it was there since the beginning of the solar system, it would have disappeared by now. So this is fresh plutonium. It's not from when the solar system formed. You can be pretty confident about that. This is fresh plutonium that was generated by the decay of uranium. Okay, 42. What is that? A beryllium-7 atom decays into... Oh, is this mass defect? Yes, it is. How much energy is produced? Yeah, that is mass defect. So maybe we should go ahead and talk about that. Okay, we'll get back to this. So let me list off the masses of the neutron and the proton before we do anything else. Let me look them up in my book real quick. They're typically in the front or back cover of a chemistry or physics textbook. Let's see. Mass of neutron. I guess I'm just going to copy down all the sig figs that I see. So mass of a neutron, m sub n, is equal to 1.00866, 1.00866, 4916 atomic mass units, which you can represent with the symbol AMU or just U, and some people will also represent it with the symbol DA for Dalton. 1 Dalton is 1 AMU. So, whatever representation you want to use. And then m sub p, the mass of a proton, is 1.007 2764 where'd it go? 67 atomic mass units. And we might need this for later. 1 atomic mass unit, I guess I'll write it over here. 1 atomic mass unit is equal to 1.66 well, I'll just keep it as 1.66 times 10 to the negative 27 kilograms. Why kilograms and not grams? Because we're going to be doing a physics-related calculation, and in physics, the standard units for mass are kilograms. We're going to be calculating joules. 1 joule is, let's see, a joule is a kilogram meter cubed per second squared. Kilograms, not grams. Wait, Is that right? Kilogram meter cubed? No, it's kilogram meters squared per second squared. That's a joule. But the point is it contains kilograms in it, not grams. So your mass units are going to need to be in kilograms when doing calculations in joules. Okay, so let's talk about this concept of mass defect. And let's actually introduce it by revisiting the first mass defect problem that we had to skip over, which was number 8. So for problem number 8 here, it says the mass of the sodium-23 atom is 22.9898 atomic mass units. Calculate its binding energy per atom in millions of electron volts and calculate its binding energy per nucleon. What on earth is binding energy? Well, turns out that the mass of a nucleus is not the sum of its parts. Turns out it's not the sum of its parts. It's usually going to be less than the sum of its parts, and that's what we call the mass defect. So where did that extra mass disappear to? What happened to it? Einstein. Delta E equals delta M times c squared, or as you know it, E equals mc squared. That's right, Einstein's famous equation. You finally get to use it. So delta E is typically going to be in joules. Delta M is typically going to be in kilograms. And c squared, that's the speed of light. Speed of light is in meters per second, and if you square it, there you go, kilogram meters squared per second squared, that's a joule. And of course there are alternative units which we'll talk about. But let's go ahead and use sodium-23 as our example. So they told us that sodium-23 has a mass of 22.9898 AMUs. So delta M is going to be the mass of the nucleus, so in this case the mass of the sodium, minus the mass of the neutrons plus the mass of the protons that are supposed to be in this sodium nucleus. Okay, well, if it's sodium-23, atomic number 11, so I know I've got 11 protons, plus 12 neutrons. I know that's what I have for sodium-23. Okay. I guess based on the fact that the mass of the sodium, I'll continue it down over here. Based on the fact that the mass of the sodium is 22.9898, so that's 4 decimal places, I guess there wouldn't be a point in going past 4 decimal places for the neutrons and protons here, since the sig fig rules are going to end us up with 4 decimals anyway. Okay, so I'm going to calculate delta M over here equals 22.9898. This is in AMUs, by the way. We're going to need to convert this to kilograms later. Minus, we've got 11 protons, so that's minus 11 times protons 1.0073 will be good enough. And also minus 12 neutrons, minus 12 times 1.0087, it looks like. Yeah. AMUs. Okay, let's figure out what that mass defect is. So we've got 22.9898 minus 11 times 1.0073 minus 12 times 1.0087 is, let me switch back to normal mode, I don't want it in scientific notation, is equal to negative 0.1949 AMUs. So the mass of the sodium is 0.1949 AMUs less than the particles it's supposed to contain. Where did that mass disappear to? It got converted into pure energy. It got converted into nuclear binding energy, to be specific. I hinted at it way back in the beginning of the video when we were talking about the strong nuclear force. Yeah, nuclear binding energy, that's the energy associated with the force it takes to keep the nucleus intact. You could say that's the tax you have to pay in order to put these neutrons and protons together. Pay some mass, get the energy required to form a stable nucleus. Okay, so converting this to kilograms, I would just multiply it by 1.66 times 10 to the negative 27, so 0.1949 times 1.66 times 10 to the negative 27. That's going to round to 3 sig figs, so 3.24 times 10 to the negative 28. So this is 3.24 times 10 to the negative 28 kilograms. That's your delta M. Well, it's negative, but yeah, so your delta E, or at least its absolute value, is going to be 3.24 times 10 to the negative 28 times the speed of light squared, 2.998 times 10 to the 8 squared. Okay, so 3.24 times 10 to the negative 28 times 2.998 times 10 to the 8 squared is going to be, rounded to 3 sig figs, that's going to be 2.91 times 10 to the negative 11 joules. Now, a more useful unit would probably be mega electron volts or giga electron volts, not typically mentioned in chemistry courses, but if you're doing physics, you might be asked to convert these in terms of millions or billions of electron volts. For chemistry, we did see the idea of the electron volt a long time ago. I think it was in video number 6, maybe. It was briefly mentioned, but let's quickly explain what an electron volt is, just in case you've forgotten. It's another unit of energy. 1 electron volt is equal to the charge of 1 electron, well, the absolute value of the charge of 1 electron, so 1.602 times 10 to the negative 19 coulombs, that's the magnitude of the electron charge, times a volt. In the previous video, we mentioned that a volt is equal to what again? 1 joule per coulomb. And so coulombs cancel out, and you get 1.602 times 10 to the negative 19 joules equals 1 electron volt. So if I were to convert this to electron volts, it's easily done. We can say 2.91 times 10 to the negative 11 joules. Multiply that by a conversion factor, so I know that 1.602 times 10 to the negative 19 joules equals 1 electron volt. And of course they wanted, what did they say again? They said calculate its binding energy per atom in millions of electron volts. A million electron volts is a mega electron volt. So we can say every 10 to the 6 electron volts is equal to 1 mega electron volt. And there we go, that's our conversion. Let's see what that turns out to be. 2.91 times 10 to the negative 11 divided by 1.602 times 10 to the negative 19. And then that divided by 10 to the 6. So rounding to 3 sig figs, that's going to be 182 mega electron volts. Okay, so that's the total nuclear binding energy for this sodium atom. Then they want the binding energy per nucleon. So this is really easy. Take the binding energy for the whole atom and divide it by the mass number. In this case, we've got 23 nucleons, 12 neutrons and 11 protons. So take your 182 mega electron volts divided by 23, an exact division, by the way. So you should still come out with 3 sig figs. That's 7.91. So it's 7.91 mega electron volts per nucleon. All right, and that's basically how you do problems with mass defect. Now, is the mass defect ever going to be positive? Well, delta M can be positive, but by definition, then it wouldn't be a defect because it wouldn't be a loss in mass, it would be a gain in mass. And yes, that can happen for bigger atoms. For bigger atoms, basically atoms that are past, let me think. I think it's all atoms past iron have positive delta M's. At least that's what I vaguely remember. I'll double check that and make sure whether or not it's true. But I do know that once you pass a certain atomic number, all atoms past that number tend to have positive delta M's, in which case, well, I'm getting ahead of myself, but it does tie into nuclear fission versus nuclear fusion and when each type is exothermic or endothermic. We'll get into that soon enough. Let's see, so that takes care of number 8. The other problem we skipped was number 17. Let me dig that up and see if it's any different from what we just did. 17, the mass of the fluorine atom is 18.99840 AMUs. Calculate its binding energy per atom in millions of electron volts and calculate its binding energy per nucleon. Okay, so basically the same process. So instead of doing that, what I do want to go over is a little bit of a shortcut. It's more commonly used in physics than in chemistry, but there's no reason why you can't use it in chemistry as well. So this whole thing, calculating everything in AMUs and then converting the AMUs to kilograms and getting joules and converting the joules to mega electron volts, it would be nice if we could streamline this process, and well, we can. We can streamline this process. So what we can do is calculate what is the delta E in mega electron volts per delta M in AMUs pretty easily. So here's what we would have to do. Let's see. So if I want my delta E in mega electron volts, let's see, delta E equals delta M times C squared. Specifically, I want how many mega electron volts is it for every 1 AMU of mass defect. So for delta M equals 1 AMU, what is delta E? That's not how you spell what. What is delta E? Technically, it should say negative 1 AMU, but you know. Okay, rather simple calculation. So 1 AMU, we can immediately substitute it with 1.66 times 10 to the negative 27 kilograms. So 1.66 times 10 to the negative 27 kilograms times the speed of light squared, 2.998 times 10 to the 8 squared. Maybe I should have done this in a different color. Yeah, I'll continue in a different color. What is the delta E associated with that? So that's going to come out in joules. Let's go ahead and calculate it. So 1.66 times 10 to the negative 27 times 2.998 times 10 to the 8 quantity squared is 1.49 times 10 to the negative 10. 1.49 times 10 to the negative 10 joules. Convert that to electron volts and then to mega electron volts. So 1.49 times 10 to the negative 10 joules equals 1.602 times 10 to the negative, well, did I say equals times 1 electron volt over 1.602 times 10 to the negative 19 joules, and then that times every 10 to the 6 electron volts is equal to 1 mega electron volt. So I guess 10 to the 6 and 10 to the negative 19, that becomes 10 to the negative 13. Okay, so 1.49 times 10 to the negative 10 divided by 1.602 times 10 to the negative 13 is about 930. And I guess I might have made a rounding mistake because it's supposed to come out to 931, but okay, let's do 930 mega electron volts. Should have come out as 931. Maybe it's because I didn't take enough sig figs with the AMU to kilogram conversion factor. Okay, so 1 AMU of mass defect is worth approximately 930 mega electron volts. This is great because now all you have to do is calculate delta M in AMUs, delta M in AMUs multiplied by 930 equals delta E in mega electron volts. Very convenient shortcut. And yeah, 1 atomic mass unit, which is approximately the mass of a neutron or a proton, is 930 mega electron volts approximately, or that's pretty close to 1,000 mega electron volts, or a giga electron volt. So yeah, if you're looking at the mass defect in terms of giga electron volts, the number of giga electron volts is approximately the number of protons or neutrons that amount of energy is equivalent to. Not something you need to know, like most things in this video, but again, more FYI for the people who want it. Before the discovery of the Higgs boson, scientists used to joke that we don't know whether or not the Higgs boson exists, but we do know that it has a mass of 126 giga electron volts. And then the Higgs boson was discovered, and yeah, it had the mass that they said it would. And by the way, even though mega and giga electron volts are units of energy, because they're equivalent to a certain amount of mass, you will hear people in the scientific community referring to particles as having a mass of however many electron volts. So don't be too thrown off by that. What they mean is a mass that would be equivalent to that much energy. In case you hear that term thrown around when exploring the subatomic particles, the bosons, the hadrons, and the mesons, and all that stuff. Maybe you'll hear about it more in physics. Okay, I think that takes care of mass defect problems. So all that's left is to talk about the processes of fission and fusion. All that's left is to talk about fission and fusion. Wait, actually, let me double check. Didn't we have... Let me double check real quick. Wasn't there a problem we had here? Oh, okay, right, 42. Hold on. We're not ready to talk about fission and fusion yet. So 42 and 43 are basically the same problem. So really it's kind of thermochemistry, but using Einstein's equation. So 42 says a beryllium-7 atom with a mass of 7.0169 AMUs decays into a lithium-7 atom with a mass of 7.0160 AMUs by electron capture. How much energy in millions of electron volts is produced by this reaction? So, same as what you've done in thermochemistry and thermodynamics. Final energy minus initial energy equals change in energy. In fact, I think I'm just going to call it delta H. You know what? No, we'll call it delta E. We'll call it delta E. So delta E equals E final minus E initial equals M final times C squared minus M initial times C squared equals delta M times C squared. No surprise there. So what was the change in mass? I think it's a very tiny amount. 7.0169 and 7.0160. So the final mass is 0.0160. The initial was 0.0169. So that's a delta M of negative 0.0009. Okay, delta M equals negative 0.0009. AMUs, and we already know that 1 AMU is 930 mega electron volts, so let's see, how do I want to do this? So delta E is going to be delta M times 930 mega electron volts per AMU, negative 0.0009 AMU times 930 mega electron volts per AMU. And I don't have enough space to close those parentheses, do I? But yeah, simple multiplication, and we're only going to end up with 1 sig fig. Yay. Negative 0.0009 times 930 is going to be about negative 0.8. Equals about negative 0.8 mega electron volts. And of course they were asking how much energy is produced or how much energy is released, which means that they want the absolute value, 0.8 mega electron volts. That's usually going to be the case. Usually they'll just want the absolute values with these types of questions. Is my camera rotated? No. Okay, there we go. That's realigned. Okay, is there anything else here that's worthy of my attention? 43 is pretty similar, so we'll skip on that. 44 is another half-life problem. Oh, interesting concept. Extinct nuclides. Ones that have had so many half-lives pass that they're literally no more. I mean, how would you know if those existed if, you know, they existed billions of years ago and they disappeared before humanity even came into existence? How would you know that they used to exist? That's an interesting question for a future Nobel Prize winner to answer, maybe. Maybe it could be you. 45. Write a balanced equation for each nuclear reaction. We already did those. 46 is the same. Okay, pass on that. Let's see. 47, more of that. We've already done it. 48. How does nuclear fission differ from nuclear fusion? Why are both of these processes exothermic? Okay, now's the time to talk about this. So, fission versus fusion. Fission versus fusion. First, let's talk about the word fission, because I personally don't like the official pronunciation. I mean, I get why it's pronounced the way it's pronounced, but when I was younger, I would pronounce it as fission, and I'm still tempted to pronounce it as fission. But I can understand why it's pronounced fission. It's because it sounds like words such as mission and passion. So I can see why the double S in fission is pronounced as an SH. But it just doesn't sound scientific when you pronounce it fission. I don't know if I'm the only person who's bothered by that, but it's something I wanted to bring up anyway. You could say I'm kind of passionate about my mission to make fission a thing. Okay, maybe those were bad puns, but there you go. It's officially pronounced fission and not fission, but honestly, I would let you get away with pronouncing it fission because fission just sounds more scientific. I don't think I'm the only one who feels that way. Anyway, the process of fission is basically the process of splitting the atom. When you bombard atoms that are already too heavy to be stable, they have too many particles in their nuclei to be stable, you basically help them split up more quickly into smaller atoms that will have a greater chance of reaching stability. So there's a visual I had ready for you. Yeah, so this is what happens when you initiate a fission process with uranium. You strike a uranium nucleus with a neutron, so that's what you see on the far left, and it splits up. It releases some energy along with two new smaller atoms, and it also produces 3 neutrons. So this is the interesting part. Since it produces 3 neutrons, if those 3 neutrons then run into some other uranium atoms, then those uranium atoms are also going to split, generate energy, and generate 9 neutrons. And then those 9 neutrons could hit 9 uranium atoms, split them, produce 2 atoms, produce energy, and produce, let's see, 9 times 3, 27 new neutrons. And this could keep on growing at a rapid pace, and eventually you're producing energy at such an alarming rate, and maybe it doesn't have enough time to escape smoothly into the surroundings, so it all goes boom. That's basically how nuclear weapons work. That's the basic idea. Lots of energy building up inside of a container, building up so rapidly that the pressure inside the container just increases super rapidly, and then all of a sudden the container just bursts, it explodes, it fractures into a bunch of pieces that fly all over the place, and yeah, basic explosive, just way deadlier depending on the amount of uranium that you put inside of it. So yeah, this is what's known as a chain reaction, because the end of one reaction produces the necessary materials to start the next iteration of the same reaction, but now it's 3 times as fast because it's 3 times as many atoms that you can hit. Of course, this all assumes that you have enough uranium atoms in the surroundings that the 3 neutrons produced from the first uranium atom splitting will actually hit them. Maybe there aren't any uranium atoms for those new neutrons to hit, or maybe there are, but they're so scattered and far apart that maybe 1 out of the 3 neutrons actually runs into one of them, and the other 2 just kind of fly off into nowhere. So you have to have a certain minimum amount of uranium, and you have to densely pack it into a tight enough space to increase the likelihood that these new neutrons will run into them. Once you have that amount of uranium, you're said to have a critical mass. You're said to have a critical mass necessary to initiate a chain reaction. So critical mass, it's the minimum mass necessary to create a sustained chain reaction. If you go above the critical mass, then you have what's known as a supercritical mass. And at that point, not only are you going to have a sustained chain reaction, it's going to grow out of control super quickly and result in deadly explosions. And of course, if you don't want your uranium to explode, then what you want to do is keep it under the critical mass. So you'd want to keep what's called a subcritical mass. I don't know what the critical mass for uranium is. It's probably a number I should know. But let's say, for example, that the critical mass is, I don't know, 1,000 grams. So if I had an 800-gram piece of uranium, I wouldn't really have to worry about any explosions happening because there's not enough uranium to produce that much energy in a short enough amount of time to cause any danger. So if I had more than the critical mass available, then what I could do is just split it up into a bunch of subcritical masses. Again, if 1,000 grams is my critical mass, and say I had 1,600 grams, I could just separate them into two 800-gram pieces and keep them separate for as long as I needed to. And if I ever wanted them to explode, then I would devise a mechanism that, brings those two pieces back together, resulting in a supercritical mass. Hit them with a neutron, and watch things go boom. Not really the type of thing that I want to think about, but some people find it impressive. I think it's just letting things go out of control. And, I prefer my stability. I prefer things staying calm and not changing at a rapid pace. And nuclear weapons are no joke. Millions of people have died because of them. But, it's good to understand the science behind things, even if they're things we don't like. If you don't like something, you still have to understand it, or else you're not going to make any improvements in the world. At least that's the way I see things. Sometimes you have to peer into the darkness. Anyway, that's the process of fission. So it's not exclusively something that happens with uranium. You can do it with other heavy radioactive elements, but uranium is the first example that comes to mind for most people when it comes to this fission process. Oh, and by the way, I forgot to show this. They do have an illustration. I don't know how good of an illustration it is for subcritical mass versus critical mass. So you can see in both cases there's a neutron in the top left corner that's going into that blue sphere, which I guess is the container in which your radioactive material is. So for the subcritical mass, neutron goes in. You see a spark, that's energy being generated, and 3 neutrons, which all lead to 3 new sparks, and eventually you have some sparks that release neutrons to the outside. You see those arrowheads that are poking outside of the blue sphere, indicating that you've lost all the neutrons that could have continued the reaction. They didn't hit their targets, so your energy generating chain reaction stops there. On the other hand, when you have a critical mass, the neutrons are going to hit their target atoms much more often, and they're going to continue hitting them for a longer period of time before they've pretty much exhausted the entire supply of your radioactive nuclei. Okay, so that's fission and critical mass. So what is fusion? Fusion is the opposite process. I know I mentioned it before. Spider-Man 2 from the original trilogy, Dr. Otto Octavius. He was trying to achieve a successful, sustained fusion reaction as an alternative energy source. And, well, we all know how that went, if you saw the movie. He failed spectacularly. So, I don't really have a visual for fusion, but let me see if I should have done this ahead of time. I should have prepared the, what do you call it? The classic fusion reaction that happens in the sun. I wish I had it memorized, but unfortunately I don't. I could probably recreate it from scratch. I know it involves tritium and deuterium. Is it in this book? If it's not, then I'll probably just have to resort to posting a link to it. Or maybe I'll try and piece it together myself. Let's see. Oh, I think I found it. Is this it? No, that doesn't look right. Oh, found it. Okay. So here's basically the process that happens inside of stars, including the sun. So you start off with 2 regular hydrogen 1 isotopes. And they form deuterium plus a positron. They form deuterium plus a positron. Then, next step, another hydrogen 1 fuses with the deuterium to form helium 3, which is not particularly stable. Helium 4 is more stable. The helium 3, once you've produced 2 of them, helium 3 interacts with some more helium 3 and produces helium 4 plus 2 hydrogens, 2 hydrogen 1s to be specific. And then one of the helium 3s, a third helium 3, will react with, wait, this isn't right, is it? Oh no, this is a different fusion process that happens in the sun. Okay, I see the alternative one down there. Should have read more carefully. But yeah, this sequence of events does occur in the sun. So taking smaller atoms and fusing them to make bigger atoms. That's basically where all natural atoms come from, and also all unnatural atoms. The way we make synthetic elements, and the reason we're able to keep discovering new elements, is because we can just ram elements into each other and get their nuclei to collide and hopefully stick long enough to make an observation, and then declare that we've created a new atom, even if it disintegrated in microseconds after it was created. Okay, so that's one fusion process that occurs in the sun. You're taking smaller elements, making bigger ones, and of course helium can then fuse and form the next element, lithium, and you can start fusing lithium to make the next element, which would be beryllium, then boron, then carbon, and so on. And that's what stars keep doing. They start by fusing the smallest atoms they have because that produces the most energy, and once they run out of hydrogen, they're forced to fuse helium, then they're forced to fuse lithium. Maybe not in that particular order. Maybe they don't wait until they run out of the smaller atoms. But, once enough of the bigger atoms have been produced and there's few of the smaller atoms remaining, you start fusing bigger and bigger atoms, and if I recall correctly, once you get to the point where a star is fusing iron, it's pretty much dying. Once a star has begun fusing iron, it's pretty much dying, because past iron, a fusion reaction is actually going to be endothermic rather than exothermic. So the energy supply is pretty much dying at that point. Anyway, back to the reaction involving tritium. I think this is the one that Dr. Octavius was trying to perform. So deuterium with tritium, those fuse to form helium plus a neutron. Helium-4 plus 1 neutron. Yeah, and I believe this is what Dr. Octavius was trying to accomplish. And you can use the delta E equals delta MC squared to verify that this is indeed an exothermic process and not an endothermic process. If you look up the atomic masses of each of these isotopes, you can definitely verify that. But that's fusion. It's the opposite of fission. So fission is exothermic for really big nuclei that are pretty much unstable. You'll have more energy when you split them into smaller atoms than you do when you keep them as big atoms. And fusion is exothermic for small atoms. If you fuse small atoms together to make bigger atoms, then overall that's going to release more energy than it consumes. So back to, oh, actually I have a graph that kind of illustrates the point at which fission becomes exothermic as opposed to fusion. Yeah, here we go. So it looks like it stops, let's see, for fusion, the binding energy per nucleon gets higher and higher and higher until you reach a mass number of, it looks like the turning point happens at around a mass number of 60. Yeah, that's about where iron is. So that makes sense to me. No, wait, mass number of 60? Yeah, that's about where iron is. So after hitting a mass number of 60, it looks like the binding energy per nucleon starts to drop after that point as you make bigger and bigger atoms. So yeah, for mass numbers below 60, fusion is exothermic. For mass numbers above 60, fission is exothermic. Approximately, of course. It's not so cut and dried, but around 60-ish is where the processes switch between being exothermic and endothermic. And yeah, that's pretty much it. There's not really anything you need to do with fission and fusion calculation-wise. I mean, you can just use the same equation we used for mass defect in order to make predictions about whether a certain fusion or fission reaction is going to be exothermic or endothermic, but outside of that, you only need to know conceptually what the two processes are. Let me see what other problems we have before we wrap things up then. So it was mentioning for problem 49. Wait, was it? Oh, no, 48. So it's asking, how does nuclear fission differ from nuclear fusion? We've pretty much explained it. They're exactly opposite processes. And then it says, why are both of these processes exothermic? They're not. They're exothermic for certain atoms and endothermic for other atoms. And the reason that we're under the impression that they're always exothermic is because we only ever care about the exothermic versions of each. Nobody is interested in splitting atoms that are not uranium or thorium or what else do we have here? Plutonium. Because if you split smaller atoms, you're going to spend more energy than you get back. It's not useful for producing energy. It's not useful to humans. At least not yet. Maybe there will come a day where it makes more sense and it's more valuable to have small atoms than it is to have energy. But right now, the big thing for humans is energy. We need lots of it. We need to generate it. We need to make it clean. And we need to run our toasters and microwaves and computers and gaming systems and everything. So, yeah, if it doesn't produce energy, we're not interested. Fusion, same thing. We're interested in fusing small atoms because that's what produces energy. We're not interested in fusion reactions for bigger atoms because they're too big. They consume more energy than they deliver. So the only fissions and fusions we care about are the exothermic ones, which is why the only ones ever mentioned you can reasonably assume are exothermic. Okay, 49. Both fusion and fission are nuclear reactions. Why is a very high temperature required for fusion but not for fission? Oh. Okay. Let's see. Fusion requires a very high temperature. Yeah, Dr. Octavius achieved that using lasers. Sorry if you find the frequent reference of the Spider-Man 2 movie to be cringy. I just think that it helps make the lesson a little bit more interesting. So, well, you need heat because in order to bring those nuclei closer to each other, their natural tendency is to repel one another because they're positively charged. So you need to overcome the electrostatic repulsion. So you do need some energy at the beginning in order to overcome that repulsion. And then once you've overcome it, once you've gotten those two or more nuclei to crash into each other and fuse into a stable new nucleus, that will release an amount of energy that is greater than the energy that you put in. Hopefully, if you used atoms that were small enough and you didn't fuse them into something that was too big. Okay, number 50. Cite the conditions necessary for a nuclear chain reaction to take place. Basically, you need to have a supercritical mass, and you need one neutron to initiate the process. Explain how it can be controlled to produce energy but not produce an explosion. Yeah, so keep it at nearly a critical mass, or actually, if you want to play it safe, maybe a slightly subcritical mass, and you'll be fine. You'll generate energy, but it won't be at such a rapid pace that it devolves into a crazy explosion like what happened with, what was that nuclear reactor in Japan? Was it the Fukushima reactor? Yeah, you don't want to have nuclear reactor meltdowns. Apparently, I heard somewhere that thorium, fission of thorium is much more stable, and they've devised a process that's meltdown proof. I don't know how much I'm inclined to believe that, but it's something worth researching if you're curious, because I don't have all the answers on thorium, but apparently people out there are touting thorium as a good alternative to uranium for generating nuclear energy. Let's see. 51, describe the components of a nuclear reactor. Yeah, that's stuff you can look up on Wikipedia if you're interested in the engineering part of it. But yeah, they have, I don't know if I could describe it accurately enough, but they have active rods which contain the radioactive material. They've got control rods, which can basically be moved up and down to block neutrons. If it feels like you're at a point where you're generating too much energy, you can use the control rods and put them in between the active rods to block neutrons and, keep things under control. You can make the fission reaction stop at any time, as long as, you're not asleep at the wheel. Let's see. So yeah, the rest of 51, you can just look it up on Wikipedia. If you really want to know the schematics, the design of a nuclear reactor core. I think it's on Wikipedia. It should be. If it's not, you can just generally Google it. It doesn't specifically have to be Wikipedia. 52, in usual practice, both a moderator and control rods. Okay, so more about the structure of a nuclear reactor core. You can look it up. 53, describe how the potential energy of uranium is converted into electrical energy in a nuclear power plant. Again, Googleable for those who are interested. 54, the mass of a hydrogen atom is that much in AMUs, tritium is that much, and that of an alpha particle is, okay, how much energy in kilojoules per mole of helium produced is released by the following fusion reaction. Okay, yeah, let's do this one. I mean, we already know how this is going to end, but, it's nice to put some numbers to the fusion process or the fission process, just to illustrate what I've been describing. Might as well put some concrete numbers to it. And also, let me check, is that the last set? No, there's one more set of problems after this. Okay. Let's switch over to here. So we've got hydrogen 1 plus tritium. Plus tritium forms helium plus a neutron. I don't know why they didn't mention the neutron there, but that's okay. Let's see, 1, 1, 1, 3, 2, 0, and... oh, wait a minute. No. We don't need a neutron. This is perfectly balanced. Okay. Then how does that differ from... oh, wait, that was a helium 3, not a tritium. Okay. And what about... and that was deuterium plus tritium. Okay, got it. So it's not the same as any of the reactions we wrote on the previous page. Where did it go? Right, so they gave us 1.007825 AMUs. That's the hydrogen 1. The tritium was 3.01605, 3.01605 AMU. Helium is 4.00150 AMU. Okay, and all of those are 5 decimal places, it looks like, except for hydrogen 1. Yeah, okay. So calculate the mass defect, or, well, the change in mass. So delta M is going to be 4.00150 minus 3.01605, also minus 1.007825. Okay, and that is 4.00150 minus 3.01605 minus 1.007825. I'm getting negative 0.02375, which has to round to 0.02238 in order to keep 5 decimal places. Okay, and that's in AMUs. And of course, we can just multiply this by 930 to get it in mega electron volts. They wanted it in kilojoules per mole, though. So I guess we're going to have to convert the mega electron volts to joules anyway. Kind of defeats the purpose of having a shortcut, but whatever. Okay, so negative 0.02238. Well, I don't need the negative anymore. We knew it was going to be exothermic. That's the only purpose of the negative sign. So 0.02238 times 930 is 20.81 mega electron volts. 20.81 mega electron volts. Let's see. And we said 1 mega electron volt was 1.602 times 10 to the negative 13 joules. Wait, did they want it in joules? No, they wanted it in kilojoules per mole. Okay, so if I convert my joules to kilojoules, that would be 1,000 joules, 1 kilojoule. Okay, so I guess that makes it 10 to the negative 16 if you divide by 1,000. Okay, 20.81 times 1.602 times 10 to the negative 16. That'll convert it to kilojoules, so that's 4 sig figs 3.334 times 10 to the negative 15. 3.334 times 10 to the negative 15 kilojoules. This is for a single atom of helium fused. So this is per atom. Per mole, we're going to need to multiply by Avogadro's number. So that's going to be 3.334 times 10 to the negative 15 kilojoules per atom times 6.022 times 10 to the 23 atoms per mole. Gives you the kilojoules per mole. Let's go ahead and multiply that out. 3.334 times 10 to the negative 15 times 6.022 times 10 to the 23rd. Let me convert that to scientific notation. That's 2.008 times 10 to the 9. Oh my goodness. 2.008 times 10 to the 9 kilojoules per mole. Yeah. 2 billion kilojoules per mole. This is why scientists are interested in fusion reactions. I mean, given this information, I think you can forgive Dr. Octavius for his obsession during the second Spider-Man movie. Okay, let's move on to one last page of problems, if there's anything relevant here. Let's go through it. 55, how can a radioactive nuclide be used to show that the equilibrium of silver chloride and water is a dynamic equilibrium? So this was actually mentioned in, I think, video number 10 or maybe video number 11. One or the other. This same exact problem. The wording is slightly different, but this problem was mentioned in one of those chapters. And yeah, if you use a radioactive isotope of either the silver or the chlorine atoms, if you use a radioactive version of either one of them, then you'll be able to detect, if you first put solid silver chloride into water and let it reach the saturation point, and let's assume that initial sample you put in had no radioactive isotopes of silver or chlorine. So, a bunch of silver ions and chloride ions, well, not a whole lot, but a few, dissolve into the water up to some maximum point, and the rest of your silver chloride stays solid. Then, if you add a little bit more solid silver chloride, but this time it contains some radioactive isotopes, and then you let it sit for a while, and then maybe you filter out the solid pieces that are undissolved in your container, and then you examine the ions that are floating around in your solution. Then you'll find that some of those ions are radioactive. You'll find that some of those ions are radioactive. You'll detect radioactivity using the tools that scientists use for that sort of thing. And what does that prove? That proves that just because the maximum amount of silver ion and chloride ion that could dissolve in the water was dissolved before you added the radioactive solid doesn't mean that those particles don't precipitate and then get exchanged with other particles from the solid. It's a dynamic equilibrium. It doesn't actually stop once you reach saturation. It continues going both ways at equal rates. So that's what that proves. I may have explained it better the first time we encountered it, whichever video that was. I don't quite remember. I'm leaning more towards video number 11. I can't see why it would be in video number 10. Now that I think about it. Number 10, video 10 didn't really involve solutions. It must have been video 11. I probably explained it better there, but at this point, I would hope that you could figure it out yourself. I would hope you'd be able to explain something like this yourself, given all the videos that we've spent talking about equilibrium and stuff. If you don't want to just go through the motions and memorize how to do chemistry mechanically and you actually want to understand it. Anyway, number 56, technetium-99. No, technetium-99M. What does the M stand for? Oh well, they'll probably explain it. Technetium-99M has a half-life of 6.01 hours. If a patient injected with technetium-99M is safe to leave the hospital once 75% of the dose has decayed, when is the patient allowed to leave? 75% decayed means 25% remaining, which means you need to cut it in half twice, which means it's 2 half-lives, so that's 12.02 hours. 2 times 6.01. That one was easy enough. And yeah, for the big exams, if you see something like this, this is something that they would definitely put on a multiple choice, and a lot of students would be fiddling with their calculators if calculators are allowed, but no, don't overthink it. 75% decayed means 25% remaining. That's one of the easy numbers. They meant for it to be easy. Don't rush to the calculator if you see something like this. Check if the numbers are easy enough to work with by hand. And finally, 57, iodine that enters the body is stored in the thyroid gland from which it is released to control growth and metabolism. The thyroid can be imaged if iodine-131 is injected into the body. In larger doses, iodine-133 is also used as a means of treating cancer of the thyroid. Iodine-131 has a half-life of 8.7 days and decays by beta emission. Write an equation for the decay. How long will it take for 95% of a dose to decay? Okay, 95%, 5% remaining. That one, you are going to have to bring out the calculator to figure it out accurately. But if you were given this on a non-calculator exam, you could still do it. You could still do it because 5% remaining, let's see. It's going to be somewhere between the 4th and 5th half-life. Because 5%, if you start at 100, one half-life gets you to 50, another gets you to 25, a third one gets you to 12.5, a fourth one gets you to 6.25, and then a fifth half-life would get you from 6.25 to 3.125%. So 5% remaining is between 3.125 and 6.25, a little closer to the 6.25. So you could estimate it pretty easily. It's going to be somewhere between 4 times the half-life and 5 times the half-life, closer to the 4. So even without a calculator, if you saw something like this on a multiple choice, you would be able to do it by hand. But yeah, outside of that, writing an equation for the decay, you already know how to do that, so we're not doing part A. I guess we can explain why you can use radioactive materials to, image parts of the body. It's actually pretty simple. It's because the radiation that comes off of these radioactive substances can penetrate through human skin and can be detected by a machine. So you can see it moving around inside the person without having to shove a camera down their veins or their throats or wherever else doctors like to stick cameras in people. I don't even want to imagine that. But yeah, hopefully they would pick something that isn't so radioactive that you get overexposed and end up getting sick because of it. I'm pretty sure they only use trace amounts to keep you safe. I shouldn't say I'm pretty sure. I'm definitely sure. Otherwise, they wouldn't be allowed to do it. They wouldn't legally be allowed to do it. Or would they? Ooh, something to think about for the average American voter. Or just the average voter in general, whichever part of the world you're in. Anyway, that's enough of me rambling. I think this is where we're going to stop for this video. So yeah, nuclear chemistry, pretty easy chapter, all things being considered. I kind of went overboard because, if it's a relatively easy chapter, you want to show off the most difficult things that you can show off so that everything else looks easy in comparison. A lot of the stuff you saw here, probably not even going to be brought up by your teacher. But it's good to know about it, just in case, especially if you want to pursue some sort of career in science, specifically in chemistry or physics. Physicists also deal with nuclear reactions and that sort of stuff. So yeah, if there's anything else I've forgotten, then I'll mention it in a pinned comment as always. aside from that, look forward to the next video, which is going to be Introduction to Organic Chemistry, not the full organic chemistry course. We don't have enough time for that, but just very, very basic organic chemistry, just introductory stuff to get you acclimated and help you decide whether or not you actually want to take the organic chemistry course in college or maybe in high school if you're lucky enough to attend a high school that actually offers the full organic chemistry course. But yeah, that's coming up next, and after organic chemistry, we'll do one last video on coordination chemistry. Well, it'll be the last tutorial video, but not the last video of the playlist. I think I'm going to do a video with my final thoughts and then like an extras video for things that were missed or things that I left out because they didn't feel appropriate to cover at the time, and recommendations for other stuff that you couldn't find in my videos. For example, I don't have a lab, so if you want lab experiments, I'm going to refer you to another playlist on YouTube that has that. You can find it yourself if you want, but you know, it'll be mentioned in an extra video, or maybe at the end of the 20th video. We'll see how it goes. Anyway, I'm gonna stop rambling here, and I'll see you guys in the next video. Wait, that's not how I wrap things up. It's been over 2 weeks now, and I've forgotten how I conclude these things. This has been Al the Tutor, reminding you once again that ignorance is not bliss. Take care, and I'll see you in the next video.